Hey everybody, welcome back to another car video. In one of my previous videos, the focus was to look at what is inside an ICE or internal combustion engine car. In this video, we'll be looking at what goes into an electric car. To understand the components in an electric car, we first need to know the difference between AC and DC. AC stands for alternating current, which is when electricity flows back and forth and its direction changes periodically. Examples of this are when you plug your phone into an electrical outlet in the wall. The electricity flows back and forth from the power grid and your phone. AC power is very common and is the most preferred electric power for household equipment in buildings. DC stands for direct current, which is when the flow of electricity does not change periodically and it only flows in one direction. Examples of this are when you don't have your phone connected to a charger. The electricity flows from the battery and provides energy for the phone to turn on. DC power is very common in electronics that have batteries in them, such as flashlights, calculators, laptops, etc. Unlike internal combustion engine cars, which have up to almost 2,000 different mechanical and electrical components, electric cars are much simpler and contain fewer components. It's been said that a modern electric vehicle only has about 20 moving parts. In an ICE car, the key component is the engine. It carries the responsibility for converting the fuel into power. That power needs to be converted into usable energy by the transmission before being sent to the drive shaft, making the wheels rotate. In an electric car, the energy comes from a large battery pack, but the main component that makes an EV special is a famous invention called the induction motor, created by Nikola Tesla in 1887. An electric motor has two main parts, the stator and rotor. The rotor is a collection of conducting bars short-circuited by end rings. A three-phase AC power input is given to the stator. This three-phase alternating current in the coils produces a rotating magnetic field. The rotating magnetic field induces current on the rotor bars to make it turn. In an induction motor, the rotor lags behind the rotating magnetic field speed, or RMF. The motor does not even have a permanent magnet or any brushes either. Despite this, it's very powerful and robust. An induction motor speed depends on the frequency of the AC power supply. If the frequency of the power supply is simply adjusted, the drive wheel speed can be adjusted. The electric motor speed can range from 0 to 18,000 RPM, which gives electric cars an advantage over ICE cars. An induction motor can work much more efficiently and produce a large amount of torque in any speed range. In contrast, an ICE car may only produce its maximum amount of torque at a certain speed range, or when the engine is at a certain RPM. For example, the Porsche 911 Turbo S only works efficiently when the engine reaches around 3,000 RPM. On average, an induction motor weighs around 32 kilograms and has a power output of 270 kilowatts, or 360 horsepower, which is roughly the same horsepower available in the Lotus Emira. This makes the power-to-weight ratio 8.5 kilowatts, or 11 horsepower per kilogram. An engine can weigh up to 180 kilograms, with a power output of 140 kilowatts, or 187 horsepower. However, this depends on which type of engine it is, whether it is twin-turboed, supercharged, or even a bigger engine. However, 187 horsepower is roughly the same horsepower available in a Mercedes-Benz A-Class, making the power-to-weight ratio 0.78 kilowatts, or 1.04 horsepower per kilogram. The induction motor receives power from a large battery pack. However, the battery produces DC power, and the motor needs AC power. To achieve this, an inverter is used to convert DC into AC. The inverter controls the AC power frequency, which helps control motor speed. The inverter can also change the amplitude of the AC power, which will control the motor power output. Although, if you don't have any electricity, the car won't be going anywhere. The electricity comes from a large battery pack, which is composed of a bunch of small lithium-ion cells. These lithium-ion cells are fairly similar to the ones you might use every day in your electronics at home. These cells are connected in series and parallel to provide power to run the car. The power produced by the electric motor is transferred to the wheels by a gearbox. In most electric cars, such as Tesla's, Volvo C40, Audi Q4 e-tron, etc., a simple single-speed transmission is used because the electric motors are efficient in a wide range of operating conditions. A single-speed gearbox gives these cars really good instant acceleration with no delay. There are a few electric cars that have a two-speed transmission. These are the Audi e-tron GT and the Porsche Taycan, which have a two-speed gearbox on the rear axle controlling the rear wheels. This gives these cars good initial acceleration at low speeds and decent acceleration at high speeds, but this has a bit more delay in speed buildup than single-speed gearboxes. However, they still have a much higher response than ICE cars. Horsepower and torque tell people how much power cars put out and how much work the engine can do. Torque is known as the turning or twisting force and is the amount of work a car can complete. Torque is measured in pound-feet or newton meters. In this video, I'll be sticking with newton meters. Horsepower is how long it takes for the car to complete said work. Electric cars generally have higher torque than horsepower. This is because electric cars are really heavy and they need to be able to complete a lot of work. The drivetrains available in an electric car are like those in petrol and diesel cars. These are front-wheel drive, rear-wheel drive, and all-wheel drive. I have explained what each of these drivetrains are in another video, but I'll explain it to you guys right now. Front-wheel drive has the vehicle only delivering power to the front wheels. In an electric car, the battery normally only provides power to one electric motor, which drives the front wheels. Examples of front-wheel drive electric cars are the entry-level Polestar 2, Chevrolet Volt, and the Chevrolet Bolt EV. Rear-wheel drive has the electric vehicle only delivering power to the rear wheels. The battery normally only sends power to one electric motor, which drives the rear wheels. Examples of rear-wheel drive electric cars are the entry-level Tesla Model 3, Porsche Taycan 4S, Volkswagen ID.3, Mercedes EQS, and the BMW i4 standard version. All-wheel drive has the vehicle's battery sending power to all four wheels. Normally, most electric cars have two electric motors, one driving the front wheels and one driving the rear wheels. Examples include the Tesla Model S, Porsche Taycan Turbo S, Audi RS e-tron GT, BMW i4 M50, Volvo C40, and many others. Although some electric cars have more than two electric motors, some have three electric motors, one driving the front wheels and two driving the rear wheels. Examples are the Tesla Roadster and Tesla Model S Plaid. Then some electric cars have four motors, which are usually hypercars, one for each wheel, such as the famous Rimac Nevada, Lotus Evija, Karma SC2, and many others. Now let's get on to acceleration, which is the main beauty of electric cars. This is where electric cars obliterate internal combustion engine cars, even the high-performance ones. Because there's no engine or gearbox which have to synchronize, no gearbox that has to shift down, no turbo lag, or engine delay, electric cars pick up on speed very quickly. It's crazy to think that a 2.3-ton Audi RS e-tron GT puts out almost 650 horsepower and 830 Nm of torque and is capable of accelerating from 0 to 60 miles per hour in 2.9 seconds. If we even look at the Tesla Model 3, which is the cheapest car Tesla's ever made, and although it may be the smallest Tesla, by no means is it slow. It puts out 450 horsepower and 660 Nm of torque, making it go from 0 to 60 miles per hour in 3.2 seconds. Electric cars can accelerate much quicker than internal combustion engine cars because they generate instantly available torque at 0 RPM and deliver it to the wheels more efficiently. In contrast, a combustion engine vehicle can lose up to 15 to 20% of its power due to mechanical inefficiency. ICE cars generally only have 30 to 40% efficiency. Electric cars have up to 80% efficiency. The more efficient a car is, the better it performs. Traction is important in every car. Traction is the amount of grip something has on a particular surface. In this case, it's the amount of grip a car tire has on the road. In an ICE car, the traction is controlled through something called ESC, which stands for Electronic Stability Control. Stability control reduces the amount of slippage of a vehicle on roads. In an ICE car, the stability control has a fairly low response. When the stability control kicks in, it cuts the car's power and then feeds the power back in to help the car smoothly get over slippery surfaces. Electric cars, on the other hand, have something called torque vectoring. Torque vectoring is when the software in the car calculates how much each tire is gripping the road. If a certain wheel is not gripping the road that well, it accelerates that specific wheel to make it stick to the road. In an ICE car, the engine has to cut the power from going to the wheels and then at a certain point feed the power back in. In electric cars, electric motors are much better at monitoring their power delivery to deal with the conditions. Electric motors don't even have to cut the power. They can just manage the power in a way that makes the car deal with the conditions perfectly. Due to electric cars having big batteries providing power to everything in the car, this makes them weigh a whole bunch. The entry-level Mercedes EQS has a 108 kWh battery pack, making the car weigh just under 2.5 tons, which is extremely heavy for a sedan. Even some of the lightest electric cars are still heavier than the average internal combustion engine car. The Lotus Evija hypercar has a 70 kWh battery, making it weigh 1,680 kilograms, which is light for an electric hypercar, but still heavier than most ICE cars. There are some disadvantages to this. Due to electric cars being so heavy, engineers have to fit the cars with stiffer suspension so that they don't lean so much on a twisty road. High amount of weight also makes the tires lose air pressure quicker and making the car have less range. The main problems that most people see in electric cars are the range, charging time, and the number of chargers available. Most manufacturers recommend that people should charge their electric cars up to a maximum of 90%, because the more you charge the battery to 100%, the battery life starts to go down, and there needs to be some space left in the battery for regenerative braking. More on that later. Some electric cars can charge really fast. For example, the Porsche Taycan has a peak power charging of 270 kilowatts. This means it can go from 0 to 80% in just 23 minutes. Some cars, on the other hand, are compatible with generic chargers and their own specific chargers. A good example is the Tesla Model 3. In general, Teslas are good in terms of their technology. Teslas are smart in determining the optimal route to take when traveling long distances because their navigation can take you through Tesla superchargers, and it's pretty easy to use. In terms of range, most electric cars have a fairly decent amount of range. The new Mercedes EQXX is known to have a range of 1,000 kilometers, which is like traveling from Detroit, Michigan to New York City. The Tesla Model 3 long range has roughly 360 miles or 580 kilometers range, which is like traveling from Toronto to Montreal. However, these are only the claimed range of the manufacturer. They would probably do much less than they're told. Brakes are really important in all vehicles. You need to be able to stop huge vehicles that weigh over 1,000 pounds. In ICE cars, when the brake pedal is pressed, it engages the brake pads, which press against the brake discs. In ICE cars, the kinetic energy in motion, gets converted into thermal or heat energy as you brake. In electric cars, there is the regenerative braking system. Regenerative braking is when the car will slow down fairly aggressively by itself, and the electric motors in the car work in reverse. The electric motors work as generators. As the car slows down, it turns the slowing down of the car into energy. The regenerative braking system recuperates the lost energy and puts it back into the battery. This makes the brake discs last longer. In most electric cars, you can usually drive with a single pedal. You don't even have to touch the brake pedal. If at some point you do need to apply the brakes in your electric car, it will slow the car down aggressively. On top of that, it still will recuperate the lost energy and put it back into the battery. Some electric cars have the capability of altering the amount of regenerative braking you get from the electric motors. Although ICE cars come loaded with computers, sensors, and a buttload of safety features, electric cars are much better at keeping the occupants away from going to the hospital. Even though the news likes to show off electric cars, especially Teslas, catching on fire, the reality is that electric cars are much less likely to catch on fire than cars that carry highly combustible liquid fuel, such as BMWs, according to Elon Musk, that is. Previously, I mentioned how heavy electric cars can be due to big batteries, but in most electric cars, the battery is mounted beneath the floor, which brings many advantages, especially in the safety sector. Due to the batteries being mounted below the passenger's feet, it creates a low center of gravity. A low center of gravity gives electric cars much more downforce, increasing traction on the wheels, and gives electric cars a much lower chance of tipping over during collisions than internal combustion engine cars. An example of this is the Tesla Model X. During crash testing of the car, it was claimed by Tesla that it was extremely difficult to make it roll onto its roof. Electric cars also have another big benefit. They have no engine under the hood. This gives these cars a larger crumble zone. If a frontal impact occurs, the force of the impact will be distributed throughout the entire structure of the car and away from the passengers. Some electric car companies, which are famous for safety, such as Tesla and Volvo, are trying to design cars in a way that can avoid causing or even being involved in a crash in the first place. They do this with the help of intelligent autopilot system, collision avoidance system, and proximity system. Anyways guys, that's going to be it for this video on electric cars. If you enjoyed, do go check out my other videos, and I shall see you in the next one. See ya!